First page of numbers. The natural numbers are the numbers that you knew when you were very young kids, 0, 1, 2, 3, 4, etc. As these examples show us, we can find the natural numbers are the positive whole numbers that are results in these simple additions and subtractions and multiplications, and the negative numbers are not natural. So let's go through a few of these. Practice our algebra and make sure we understand what natural numbers are. Find the value of these expressions when a equals 2 and b equals 4. So you're just substituting in here. A equals 2, so 2 times a plus b, which is 4, is equal to 4 plus 4, which is 8. And then you state whether they're natural numbers or not. Yes, natural. Okay. What about number 2? 2 times 2 plus 4. So we're going to do the parentheses first. So 2 plus 4 is 6. 2 times 6 is 12. Natural number also. Do you see the difference between this and this? The parentheses mean that you do the 2 plus 4 before you do the multiplication by 2. And this one says to do the multiplication by 2 first, just with the 2, and then add the 4. And that's why you get the different results, 8 and 12. What about a squared minus b squared? So that would be 2 squared minus 4 squared. And the minus sign is done last. You see the exponent comes before the subtraction because PEMDAS E comes before S. So this is going to be 4 minus 16. It's going to be negative 12. Negative 12 is not a natural number. What about the last one? A minus b and then quantity squared. So 2 minus 4 quantity squared. So that's going to be negative 2 in parentheses squared. So the negative also is squared, so you end up with 4. There's the difference between doing negative 2 squared with no parentheses and negative 2 squared with parentheses. In this case, the 2 comes first, the exponent comes first because there's no parentheses to indicate otherwise. It would be negative 4. This would be negative 2 quantity squared, so the negative would also be squared, so you would get positive 4. Okay? So in this case, it would be positive 4, which is a natural number. Alright, solve the equation 4x plus 2 equals 0. State whether or not your solution to part A is an integer. Okay, so we're going to solve it, which means we're going to find what x equals. Well, this is just pretty easy algebra. We're going to subtract 2 from both sides, and we're going to end up with 4x equals negative 2. Then we're going to divide both sides by 4, and we're going to get x equals negative 1/2 because the left side of the 4's cancel out. So, is this an integer? No, not an integer. So we could say it's not an element of z. Let's write this in better math. We could say negative 1/2 is not an element of z, the set z. Solve the equation x squared equals 4. State whether or not your solutions to part A are integers. Well, x squared equals 4, you're going to take the square root of both sides. When you take the square root of both sides, you are actually saying it could be plus or minus 4, square root of 4, which would be plus or minus 2. So the answer could be plus 2 or minus 2. Okay? And because remember, plus 2 squared is 4. Negative 2 squared is also positive 4. State whether or not your solutions to part A are integers. Yes, plus 2 and negative 2 are both members of the set z, or integers. Find the value of these expressions when a equals negative 2 and b equals 4. Okay. When you have this, remember that whenever you have this horizontal line, it means division. Not only does it mean division, but it means parentheses around the numerator and the denominator. So let's see, instead of a minus b, we're going to write negative 2 minus 4. Instead of a plus b, we're going to write negative 2 plus 4. And then we're going to say the top is negative 6 and the bottom is positive 2, and then we end up with negative 3. Okay. And then is that an integer? Yes, it's an element of the set of integers. Now let's do the second one. 3a squared minus 9 over b. So 3 times negative 2 squared. Do you see when we substitute a equals negative 2 into a squared, we put it into parentheses, minus 9 over b, 9 over 4. Okay? And then negative 2 quantity squared is positive 4, so that's going to be 12 minus 9 fourths. So that's going to be equal to, if you make 12 into a fraction with a common denominator of 4, it's going to be 48 over 4. Minus 9 fourths, 48 minus 9 is equal to 39 fourths, which is not an integer, right? Not an integer. Okay? So that's it for page 1. Now we're going to do page 2. We're going to talk about the rational number set, which is Q. The rational number set means that all the numbers that you can form by taking one integer and dividing by another integer, except for you would never divide by 0. Okay? Let's see. Remember that numbers that can be written as integer divided by integer aren't necessarily decimals that don't go on forever. For example, like 2/3 or 6 over 9 is like 0.666 going on forever. The thing is, 0.666 is a repeating pattern. And whenever it's a repeating pattern, you can write that as a fraction or a ratio of two whole numbers. Okay? Whereas there are other numbers, irrational numbers, which cannot be written as a ratio of two whole numbers, such as square root of 2 or pi. Okay? So that's the difference between, or that's the nuance of, repeating decimals going on forever, and irrational numbers. Okay, 1a. Find the decimal expansion of these fractions. After you do that, then we just want to find out if it's a finite number or a finite decimal, so it ends, becomes 0 after a while, or it recurs. It repeats for a while, but then it just it repeats forever. Okay? So we can just do these on our calculator. So let's do negative 5 divided by 4. Negative 5 divided by 4. Oops. Negative 5 divided by 4. Negative 1.25. Is that finite or does it recur? It's finite because it just stops with the 5, right? Now we're going to do 2 divided by 9, which is the next one. Oops. 2 divided by 9. 0.2 going on forever. Okay? That is recurring, right? It repeats the pattern 2 over and over again. Next one, 4 divided by 7. 0.5714285714. Do you see how it eventually repeats? 571428, and then it repeats. The way we could say that it repeats is you could put dots over all the numbers that repeat, or you could put a long bar around the pattern that repeats. So this means 571428 repeats over and over again. So this is a recurring or repeating decimal. Finally, negative 11 fifths. Negative 2.2. So this one is finite, right? Okay. Here's the other notation you might use to show a repeating decimal. You could put a dot over the digits that repeat. So express dot 55555 as a fraction. Okay. Now there's a trick you can do with this with the calculator. Let's see. You could put it into mode. And I'm going to say I want the output to be a fraction. So I go to answers and then I go to fraction. Okay, and then I'm going to enter this decimal here as best as I can.
So I'm just going to put a whole bunch of 5s. It repeats forever, and I can't put it forever, but I'll go as far as I can. Then I'll hit enter. And you see how the calculator changes that to a fraction? So even though we didn't put in 5 an infinite number of times, as long as we put it in about 20 times, it's enough to fool the calculator into thinking that's 5 going on forever. I can do the same thing with 1.88888. Let's see, I'm going to write that as a fraction too. So I just hit 8 a bunch of times, hit enter, 17/9. Okay, now I'm going to calculate 0.5555 plus 1.8888, and I can do that also by just like typing it a bunch of times. Or, I could just do fraction arithmetic. Now that I know that one is 5/9 and I know the other one is 17/9, I could just add the numerators together to get 22/9, right? 5 plus 17 is 22, so the numerator would be 22, the bottom is 9. Okay? Alright, number 3. Write down a rational number whose definite decimal expansion is finite. Okay, so for example, 2.5, right? Write down a rational number whose decimal expansion recurs. So we could put 2.5 repeating forever. Write down a rational number whose decimal expansion has a period that starts, and when they say period, they don't mean like a period like a decimal point, they mean like a repeating pattern. A period that starts in the 4th digit after the decimal point. So we could have 2.567, and then we could have 9999, right? We could have 9 repeating after that, for example. Or it might be something more complicated. It might be 2.567, 923, 923, 923, and we could write that by putting a horizontal line over the 923. Okay, so those are 2 possible answers. Finally, write down the 3 rational numbers that lie on the number line. Write down 3 rational numbers that lie on the number line between 2 and 9/4. So there's 2, and there's 9/4, and just so that we can see what 9/4 is, we're going to put the mode back to decimal. So mode, and then we're going to go down here and we're going to change to decimal output. And then we're going to say, oh, what was 9/4 in decimal? Oh, yes, 2.25. So give me 3 rational numbers that are between 2 and 2.25. So that's easy, right? You can put 2.1, 2.2. What's another one? Oh, 2.15. Okay, and that's it for page 1 and page 2.